Hello there, thank you for joining me again today on another video of radio frequency test equipment, being a spectrum analyzer, the HP8560E, and today we're joined by the technical manager who will be directing me today on all things technical regarding this instrument, and decided to make an introduction in this video. So without further ado, we'll get straight on with the video. The spectrum analyzer that we have before us today is manufactured by HP8560E. If you've seen my other videos, you will by now have seen how we do measurements with spectrum analyzers, measuring frequency, amplitude, deviation, amplitude modulation. If we're not looking at FM frequency modulation, we look at AM, SSB, and we make measurements of RF signals using those instruments. Today this instrument is slightly different from previous videos that we've dealt with, in the context that this particular instrument has the tracking generator option installed on this particular spectrum analyzer, so we can extend the operational use of this instrument into lots of other avenues that other spectrum analyzers that don't have a tracking gen on have limitations, whereas this has more of a useful capability when it comes to testing things like filters, aligning duplexer filters, bandpass filters, measuring the attenuators, for example, gain of many devices that can be looked at, phase noise. We can look at the performance of RF cables, all sorts of different applications that the spectrum analyzer can go into. The 8560 series of spectrum analyzers, which this is from HP8560, it's quite a popular instrument. It's been around for many years. There's the 8560A and E models and all sorts of variants of this, some with and without the tracking gen option, with different options as well. When we have a look at the back panel, you'll see some of the other options that are enabled on this instrument to allow more flexibility when connecting to other instruments, and the capabilities that it has for extended use. But what we'll do in this video, we'll just go into first of all the basics of spectrum analyzers, doing measurements, the safety concerns regarding how not to damage a spectrum analyzer and how to measure signals properly, and indeed we'll also look at the configuration and settings of the instrument and how we will set up the instrument to perform certain measurements, including looking at doing actual measurements with filters, and in conjunction with other test equipment by providing signals into it, so that we can detail and look at signals on the screen and measure them properly. 3 dB points, peaks. We use a track gen. We'll also look at delta markers and how we use them, and we'll go into all the different menus and what all the functions consist of. And there is a lot of menus on this instrument, which can often be very confusing to the first time user when it comes to, you know, dealing with such an instrument, because they often use terms that are not easily understandable. Unless you're experienced or use the instrument commonly, you might find it difficult to drive and understand, and the calibration of the instrument and also the settings and how you set the instrument up can have a detrimental effect of how it will perform a measurement. And I've got some specific examples that I'll show as well with this, where I had a friend who also owns a very similar model. It was the A model, whereas this is the E, and he couldn't get the track gen to work properly, and there was a setting that it could go into to sort of recalibrate the track gen so that it finds its peak, and because he'd not done that, he was convinced that the measurement of the filter that he was looking at was wrong, as in the filter had a problem. so it can lead you down the garden path if you're not familiar with how to set it up. So that's what we're going to do in this video, so stay tuned and we'll get into it. Okay, right, we're back. Okay, so let's just have a look at the front of the instrument just to familiarise ourselves with how it operates. The three main modes that you'll use on the spectrometer will be frequency, span and amplitude. They're the three main things, despite all the bells and whistles that you see on this side and all the data entry keys and everything else. They're the three main functions that you tend to use on the spectrum analyzer. The other bits are all extra functions, capability, utilities, menus and functionality that we'll go into at a deeper level in this video. But just the basics of it. One of the nice things about the HP Agilent spectrum analyzers, if you mess it up, you can just press the green button there to preset it, and basically it just then sets it back to, you know, a default manufacturer's settings, and then you can go right back to the start again, because it is quite easy when you go into different menus and setting different things up. It affects things. If you've got the span very wide and you select a frequency that's way down here and you input a frequency directly, because the span's very wide and its accuracy is quite precise, is that until you narrow the span down and pull out a frequency further to examine it, then you can find yourself where the frequency readout will change slightly above what you've already entered in with the frequency key. And they're little things that are quirks with spectrum analyzers that you tend to find because you've not realised that you've got the span very wide. You're trying to look at a frequency that's appeared on the scope, and because the span's extremely wide, that in order to pull out the accuracy of the frequency of that signal, you need to narrow the span down further. And so often what happens is, as part of that routine of doing that measurement, that you can lead yourself down a garden path where it will actually select or appear to select a frequency that's not the frequency that you've entered in originally, and that's normal with most spectrum analyzers. It's just a case of retracing your steps and going over things. It can be a little confusing at first, but you'll see that in a moment when I go into doing measurements. Now, regards to the input sockets on the front, and obviously the rated specification of this instrument, the input's 50 ohms. It often tells you the frequency range starting to what the instrument's capable of doing, but it also gives you some warning information which needs to be heeded. Here it says 0 volts DC maximum and plus 30 dBm or 1 watt maximum. So on the left here, this is mainly concerning DC bias. A typical example of DC bias would be, for example, when you're looking at a microwave radio link, for example, an outdoor microwave radio link, the dish that's on the microwave tower, on the RF tower, radio tower, is often fed up a piece of RF coax, 48 volts DC, and superimposed on that supply in the coax as well is the RF signal, the IF output of the microwave link. That comes down the radio tower into the equipment cabin at the bottom, where it meets with another unit in a rack, which is called an IDU, an indoor unit. And so the IDU splits off basically the supply that it gives the microwave dish or the microwave transceiver on the tower and the RF signal, and then processes the RF signal, the IF. So for example, if you've got a 38 GHz microwave link, the IF might be in the UHF frequency range, it could be VHF, it could also be at 1.5 GHz, 2 GHz, something like that, depends on the manufacturer. And you might want to sniff part of that off here and read that out on the spectrum analyzer. But the trouble is that if you don't take account of blocking the DC, the 48 volts supply that goes up the coax to the microwave dish on the tower, then you're going to feed 48 volts DC into here. It's going to blow the instrument. So what you need to do when you're looking at any amplifier microwave link, any device that needs a DC bias fed up, like a masted amp, a gas FET amplifier, or a mimic amplifier that uses DC feed up the coaxial cable, you must always put a DC block in, and that's a device that looks like an RF attenuator that we'll look at later on in the video, which connects here and prevents, basically, it's got a capacitor in it. It prevents DC from getting to this socket, but it allows the RF signal to pass through. So in that case, that example that I've given you, the microwave link, 48 volts, doesn't end up here in this port and damage the instrument. Likewise, the warning on the right about the plus 30 dBm 1 watt maximum, that appertains to RF, radio frequency energy, coming into that port. You mustn't exceed that level. I certainly wouldn't even go to that level, because that's a damage level, is 1 watt maximum. I wouldn't even put 500 milliwatts in. You know, I'd be using it well below half its rated input, so that it wouldn't cause any damage to the instrument. There are ways and means of measuring RF signals, even high-powered signals, which I'll go into, using attenuators, RF power attenuators, and also indeed sniffing through couplers, where we're sniffing high-level RF and just getting a little sniff of it to then analyse here, and then we can then measure things safely. We've got a cal output as well on here, which we use periodically to calibrate the instrument. It has its own calibration routine. The cable connects from here to there, and we use the cal button, which is just there in the centre of the screen on the top row. That button then takes us into a detailed menu, which allows us to calibrate the instrument's internal modules and frequency stability levels, and it's basically its analytics are all calibrated via these two ports being connected together. I'll go into that later on as well. We've got a volume control here, which is for use for demodulating the whatever signal we're looking at on the scope. So this particular instrument has a capability to demodulate FM and AM, and again we'll look at that later, but it gives you the opportunity then to listen to the signal and what modulation's on it, which is quite useful. This is the first local oscillator output, which is terminated into 50 ohms, which is this SMA 50 ohm load that's on the end. When that's unscrewed, we can connect that off to other instruments to measure the first local oscillator output, which is useful in many different applications. Again, we'll look at that later in the video. And this little feature here is the RF output, basically giving us the frequency range again of 300 kilohertz to 2.9 gigahertz. This again has a warning. This allows 30 volts DC bias there, and a plus 30 dBm or 1 watt maximum reverse power. Again, any exceeding above that would cause damage here. And then we've got the power switch here as well, for turning the mains on and off. So that option is a track gen output where it says RF out, so that allows us to couple a signal out to measure, for example, the performance of duplexer filters, bandpass filters, low noise amplifiers, attenuators, many different things, including RF coaxial cables, you know, what losses are incurred in that. So many uses is the track gen output that comes out of there. So that's an output and that's an input. You'll notice there's a slight difference between them in the fact that this is 30 Hz to 2.9 gigahertz on the input, but then on the track gen output it's actually 300 kilohertz to 2.9 gigahertz. So it starts at 300,000 hertz, not 30 hertz as previous on the input port there. So worth bearing in mind. This little socket here is for feeding a power probe in. Hewlett-Packard do a range of sensors which allow you to read radio frequency, RF energy direct into there. So they do accessories. I don't have those, but you can buy those to connect in there. They have an active probe as well, which you can get power from this socket, because that's what it is. It's a powered probe, and they connect into there, and they obviously do EMI measurements and things like that as well, which can go into there, and EMC, electromagnetic compatibility, like active probes and things. All kinds of different accessories that HP Agilent do. Amplifiers as well for increasing the input sensitivity. They get their power from there too. One of the nice things about the HP analyzers on all their range is that they have this green button here which you can press. Should you make any errors or mistakes, it's quite easy to do that, so you can just press preset and then click last state, and then basically put it back to manufacturer's settings. The three main functions that are obviously used on any spectrum analyzer, no matter what you're looking at, is frequency, span and amplitude. So obviously we can input a frequency directly if we know what it is. We can increase or decrease the span, so we can pull out one signal or look at many signals, and the amplitude sets up the RF attenuator, how sensitive or how desensitive this is, by selecting the amplitude, and then we can pull out a signal and look at it in greater detail, and attenuate a signal as well that might be quite high level coming in there. Naturally, when we talk about levels, and we've just spoken about this only being able to accept a maximum of 1 watt port, 1 watt RF, is the fact that the one of the common mistakes that people make on these is by feeding in a transmitter directly into that port, and 25 watts, 40 watts, whatever the power be, blow the instrument straight away. And likewise, you know, even a handheld radio doing 4 watts or 2 watts would blow it. So again, we'll talk about as I mentioned earlier, about measuring RF signals correctly. You've got to be very careful with the spectrum analyzers. It's extremely easy to damage them if you're not really au fait with what you do and how you should measure things correctly with them. Obviously, we've got all kinds of different menus and things here, and control markers and data entry keys, as well as the knob rotary control that we can use. We've got menu keys here at the right hand side of a display, which when we go into certain options it will allow us to access certain menus and to drive the machine that way. There are plenty of sockets on the rear of the unit as well that we'll go into towards the back end of the video when we look at the features and options that are on the instrument, and that too will show you the extended capability of what you can do with this instrument, particularly if you're looking at oscillators and things where you can sweep an external oscillator, and obviously read the performance of that on this device. So right, we'll get straight into doing a measurement now. Okay, we're back now with ready to do a measurement. We've set up the HP8560E radio test set down there as RX test on a signal generator, outputting a certain frequency at a certain level. So the idea now in this exercise is to find the frequency on here. Now, if we look at the display very carefully, we can see that we do already have what appears to be a signal right at the far left, even though we've not connected anything in to the input. This is basically a common thing with the HP spectrum analyzers, that you'll see when you're measuring signals. There'll be another one below it to the left, and that's basically it picking itself up. It's at 0 Hertz, 0 frequency, so it's not something to be concerned with, but it's something to be aware of, and that occurs on most of these HP spectrum analyzers. So if we connect the RF signal to the input port, we can see we've got a myriad of signals now that have appeared, and obviously looking at that, we need to try and reduce the unwanted signals down so we can have a look at the fundamental signals. At the moment, the center line or the center frequency is at 1.45 gigahertz, so that's quite a high frequency. We can't really see any large signals further up this part of the display, but they all seem to be ramped up to that left side of the display. So we can do a multitude of things now to try and find that. We can either manually input frequencies lower down. If we know it's a VHF signal that we're looking at, for example, we can enter in a VHF frequency and then open the span up to cover most of the VHF range from near enough 0 to 300 megahertz, and then pull out signals from that there. Or we can put a UHF frequency range, that's a 300 to 1 gigahertz, to pull out the UHF spectrum. So it depends how much information we're already armed with. Or we can use the markers menu here, where we can do peak find, and it will find the highest level of signal that's coming in on this port and show that frequency. So for example, I could put in a spot frequency, say, of just guessing here, we could put in a spot frequency of 300 megahertz. Okay. The span currently what we're looking at is 800 megahertz wide, so from there to there is 800 megahertz. We could reduce the span. We can see some signals here. We can see a large signal there and then a smaller signal there. We can do two things now. We can reduce the span further, so we're pulling out these further so we can get more details to what the frequencies are on these. Or alternatively, we can go frequency, marker, and then highlight the normal marker. We've got a little ball, little dot, and then as we change this marker, as we move a marker, then the frequency will be displayed there. Now this is where some inaccuracies can occur, because we've got such a wide span of 800 megahertz. If I go down to there, that's highlighted a frequency, the highest level there in particular, at 145 point, I think that says 9 megahertz or 3 megahertz, 145.3. Now at that stage that's not an accurate frequency readout. It's near it, but it isn't actually the frequency that's coming in. I know that because I know what frequency is coming in. But from your point of view, if you were looking at a signal, that isn't the accurate frequency. When you've got the span set so wide, it can get near the frequency that you think it might be on, but it won't be the exact frequency, and that will become apparent. So if we keep that in mind, that we've got 145.3 megahertz there, it says at 0.67 dBm, then what we can do is we can now pull that out. So bearing in mind that says 145.3, if we do frequency now, because these are harmonics, these are lower level signals, we don't need to look at these in this context. This here is another signal, but I think you'll find when I disconnect the RF that'll still be there, and that's often what's found on HP spectrum analyzers. That can lead you a little bit of a merry dance, can that, if you're not careful. But if we take the marker to that, you'll see the reasons why that can be ignored. So if we move the marker down, you can see it's at a very low frequency. It's basically at 0 hertz. It says 1.3 megahertz there, but that's because we've got the span so wide. But basically that's an internally generated signal. It's just basically where it's starting from, the spectrum analyzer. So yeah, that gives you a little bit of a false indication that there's something there, and it isn't. It's just can be ignored, but you'll find that on a lot of the HP spectrum analyzers they all tend to suffer with that, and it's normal. So the largest signal is that one. There is another way to find the signal. If we've got that scope as we've seen it there where we were to start with, you can do what's called peak find or peak search. So if I now press that button then it will automatically find the peak. Now obviously if a signal disappears, this is where you can get a bit sort of taken off down the garden path. If you're dealing with something where the signal's gone and then you did, for example, its amplitude are reduced, and then you did for example peak search, then depending on whether you're setting it for this frequency, it will find sometimes the lower level signal, and it will go for that, and then what will happen is then it'll highlight that signal sometimes, and you'll then be drawn off to look at that as being your fundamental signal, and it'll pull that in. Some of the other spectrum analyzers that I've got have a search capability, where it'll do a frequency search, and that's certainly on the other model spectrum analyzer from HP that I've got, and it will keep scanning until it finds a peak. So the moment you remove the RF input, it'll then find its internally generated signal and go to that, and then you'll find, unless you keep your eye on the frequencies of where the marker is, you'll find it'll have wandered off onto its own internally generated signal, and you'll be for a while scratching your head trying to work out why, when you turn a transmitter on and off, the signal's not disappearing, and you'll find that it'll have wandered off onto the internally generated frequency. So it can get a little bit frustrating at times, but you get used to these little quirks with these spectrum analyzers. So we've reintroduced the signal now, and then basically what we can do is we can do again a peak search, and then it'll find that peak. We can then go to span, and instead of having it at 300 megahertz or 800 megahertz as it is here, we can perhaps reduce it now. Bear in mind it says it's 140, where was it now, frequency, and center frequency, oh, marker, there we are, look. 145.3 megahertz it says at 0.67 dBm. So if I then change the span now, so we make it 10 megahertz, okay, now we'll have to put the frequency in. If you've noticed, it's altered its frequency to 299.67 megahertz. So again, that's another thing where you think, oh well, I've looked at that frequency, I'd like to, you know, obviously reduce the span, but what you've forgotten is that the center line of that display prior was 800 megahertz. So again, that's another error that you can make, is that you can think that you can pull out signals in the screen and span, here we are, look, 800 megahertz, we'll get that back. So right in the middle is obviously 400 megahertz here, and the total span is 800 megahertz. The center frequency is 300 megahertz rather. I was wrong in saying it was 400, it's actually 300 megahertz. So you can then go to marker or peak search, assuming it's that, then you can do marker to center frequency, so it'll drag that to here, marker to center frequency. Bearing in mind it says 145.3 megahertz now is the center frequency, and then you can do your span to pull that out. We'll set 10 megahertz, and now we're pulling that out. And as you can see where the marker is now, it's on the right side of that signal, so that just shows you how inaccurate the previous measurement was. Now if I go back to marker again and move a marker, and we keep an eye on the frequency up here, you'll notice it's on, the signal is actually on 145 megahertz dead, not 145.3, and that's because now we've narrowed the span, so we've pulled out the signal more, then the accuracy of the instrument improves. So that's what you've got to be careful of, is that sometimes when you're looking at a full span, if for example it says you're 145.1 and you went down to say a 10 kHz span or a 100 kHz span, then it wouldn't show the signal in the display at all, and you'd have to widen the span a bit more till you see the signal, and then you'd have to then grab it, move it to centre frequency, and then reduce the span again so it pulls it out. And that's just one of the quirks with spectrum analysers, where if you've got the span set too wide, the actual detail of the signal and what its frequency is can be inaccurate until you've pulled it out a bit more and sort of homed in on that one signal a little bit more than you would have done prior. So now we can see a level, it's on the top line. We can now adjust the amplitude, just so that if it's too far up like that, it can't measure the signal properly. So you need the peak of the signal to be below or at the top line there, for example, and then it'll read the level properly in RF level. Now I'm outputting a signal from the test set over there at 0 dBm, so that's reading almost correct, and then the frequency I'm giving out is 145 megahertz. So that gives you a little idea of how to pull signals out from a measurement. That's just sort of the basics of it, in order to home in on something and then obviously pull that out. Now if we go back to where we were before, if we increase the span now to 800 megahertz, when we looked at that, we had the internally generated signal, the fundamental frequency, which is what we're wanting to look at, and then we have these harmonics, and they're a product obviously of the fundamental frequency, so they're multiples, and that's obviously why we were getting these signals here in the earlier measurements, because obviously this is, you know, harmonic content of that signal, and these are the harmonics obviously going up the frequency range, so they're normal, but again that's why you see these signals, because these are the harmonic content of a fundamental. So obviously that's it for this part of the video. I'll now move on to the other parts of the measurements that we can do. Now, in regard to finding frequencies as well, there is another way that you can deal with that. If we preset the instrument back to what it was prior, if we're inputting a frequency or given a piece of equipment that we know operates within a certain frequency range, say for VHF for argument's sake, what you can do, if you want to just try and, instead of looking at, for example, you know, you could be feeding in a signal here that's likes to scope up completely with frequencies everywhere, because it's an input from an antenna on a radio tower, and it may be that it's an amplified signal that you're wanting to look at interference nearby, for example, but you know it's in the VHF frequency range. You can actually, if you go to frequency, you can do a start frequency and a stop frequency. So you could say, for example, you wanted to start at 100 megahertz and then stop at 200 megahertz, for example. Then naturally, you know, with that frequency span, you're starting there at 100 and stopping at 200. So anything in between there, we're gonna see that on the spectrum analyzer, and as we can see, we've got a signal there. And obviously that allows you to do that. Now there are obviously there are other functions that you can go into as well, where you can look at multiple signals and compare them and pull them together, which you can do in those menus. But that's another way of being able to home in on a certain part of the radio spectrum and then narrow it down into a particular frequency that you're interested in looking at. So it all depends on the application, obviously, as well. So right, we'll do the other measurements. Okay, while we're still in the frequency modes, if I go to marker, we have a range of different marker functions that's available. So for example, we can go to delta marker, and that uses the point at the moment where the marker is as a reference, and then when we move from there, then we'll get a readout, for example, of what frequency that is and the level. That's often used for finding such as the 3 dB points of a signal, and then you can find out what frequencies that will be for calculating things like bandwidth in filters and things, which we'll go into a bit later in more in depth. Now, as far as you can look at, for example, multiple signals as well, which we'll look at. There's marker noise as well. There's signal track on and off. Markers off mode, so you can just get the full screen if that's what you want. But in addition to that, there's quite a few features which I'll show you shortly, where we can look at a signal and then alter its state, like for example introducing modulation, and then we can physically look at its signal after we've applied modulation and compare the two, so you get two waveforms on the screen. So there's quite a bit that you can look at. But in the span, if I were to say 100 kilohertz, for example, let's try 300 kilohertz, and then we were to go to frequency, just that for the middle, we can measure the RF level, which we know in certain examples. For example, if you've got a test set that you're looking at, the accuracy of what level that's giving out, for example, if you're entering 0 dBm output on there, you want to check that the level's correct coming out of it, which will be shown there. And how you get that accuracy is to narrow the span down. I'm at 300 kilohertz there, so that you've got a good resolution of the signal, and then you can put your marker right at the peak, and you can do that by obviously doing your peak search, so it'll get the optimum peak, and then we can adjust the RF level. So I can then check the calibration, for example, of so if I select minus 20 dBm on the radio test set here, and just check that it's more or less in calibration there by looking at the signal there. And of course that's where we're looking at the amplitude, or the level of the signal. And again, in this particular case, I'm using that in the context of checking that instrument is giving the same or the correct output level that it says on the screen, and we're checking it here to make sure that not only is the frequency accurate, but the level's accurate too. So that's an example there where we can check that. Now, another way to check that is under span, and then select 0 span. So that basically takes that peak of that signal, and we're widening the whole thing out now. We've basically got no span at all. We're just looking at that pinpoint right at the top. Now, if I were to, for example, demonstrate that by selecting frequency and then tuning off that frequency, you'll see the level starts to fall, because now we're coming off that slope on the left side. We're coming down it now, so obviously the RF level begins to fall with it. Likewise, if I increase the frequency, we come to the peak, and then we will then begin to fall again, because now we'll be slipping down the right side of the waveform that we could see earlier. And so we can measure it's a more accurate way of measuring the peak level of that RF signal, and that's basically, you know, what we can do. Now, last span, so we're looking at that level there. So because we can pull the signal out, modulation on it as well, and measure the signal as well. And there's a good reason for doing it like that as well, because it gives you more accuracy when you apply modulation like we're doing now. And then for example, we can reduce the span to 1 megahertz, for example, or even less than that, or 100 kilohertz. Now we can begin to see the effects of frequency modulation on the carrier, and with that then you can do further measurements where you can you know, if you wanted to pull out the level with 0 span, then you can measure the level even with mod on it as well, which is quite useful. So that's another example of it. Last span. And in this particular context now we can also see the modulation content that's on the carrier as well. So I can reduce the span again, and then we can pull that out, you know. So we're introducing try and get it in the center frequency of the screen, and what we're doing there is we're pulling out now the signal. We can see the 1 kilohertz frequency that's been modulated on the signal, as well as the side bands, and we can also see the total width of the signal as well. So if we enter that frequency again of 145 megahertz, just so we get it bang in the middle, and we can see then with this measurement, we're measuring the amplitude of the signal, how high the signal is in amplitude, as well as the bandwidth, or the width of the signal. And so we can go back to markers, and we can do a normal marker, and then we can move a marker literally, and check the width of the signal or the deviation or any point of this using the markers. So that's another way of being able to measure. And obviously there's a delta marker, so you can do peak find, peak search. It'll always pick out whichever peak at that moment in time is the highest, and then you could do your marker delta, for example, and you can move it from there. Because it's very low resolution at the moment, it takes a while for us to be able to move it and make then the comparisons. You can then go to next peak and keep going down, and you can look at any part of the signal that way as well. So lots of advanced features. You can really get in depth into it if you really want to look at a signal. So next we'll move on to more options that you can do in span, but there's quite a bit there, as you can see, the frequency section. So in the span you've either got span zoom, full span, 0 span. As I say, 0 span's used for really pulling out that signal peak to absolute 0 and showing us what level is that at that signal point is, so that we can measure the level of RF, for example. And then you've got the last span if you want to go back to where you were before. On the amplitude side of things, we've also got the reference level, so that's set at the moment to 0 dBm. So the top line is at 0 dBm here, and then you've got the attenuator, auto manual, you've got logarithmic or dB per divisions, you've got linear, then you've also got reference level offset as well, if you're using things like external attenuators, or you're offsetting the level for whatever reason that may be. You've got the maximum marker level as well, and then you've got units that you can measure in, whether it's dBm, dB microvolts, dB millivolts, volts, watts, for example. So power level there, where it says PL, it says 1 milliwatts, which is 0 dBm. So there's lots of different menus and sub-menus. There's quite a bit to it. That's power level, we've been into that. Normal reference. As I say, if ever you're dealing with the test measurement and you get stuck and you mess it up, you can just hit the green button, the preset button, and it'll take you back to where you were. Okay, so now that we've done span and frequency and such like, and all the markers as well that we've got here, and we've explained that, obviously we've got the different types of span menus here, which we went into a moment ago. The next thing I want to talk about is amplitude, and that's again one of the three main functions of the instrument as well, is that there will be times when if we're particularly measuring high powered signals that are coming into the front port here, that the attenuator will need to be adjusted because the signal will be just literally off the screen. And so we can do that using the step keys or the rotary control, and we can adjust the attenuation appropriately so that we can, if you like, make the instrument more susceptible to weaker signals or stronger signals, and obviously then we can adjust the attenuation that way. Now we can do such a lot at this stage, which is quite important, because if we allow the signal to be too high, so it's literally off the screen, you know, it's sort of like this, for example, you may find that when you open the span, we'll just open that up to 100 megahertz, you may get, we'll try 1 gigahertz, lots of harmonics and unwanted signals as well, which you'll see will appear. But when we then reduce the signal level to a what is a high attenuation, then those tend to go away, and that's because we're overdriving the mixer inside the instrument. So it's important when you make measurements that you make them with the correct amplitude in mind as well, where the signal isn't, you know, off the top of the screen, that we get it at least below the top line, so that we can make sure that the mixer internally is not overloaded, and therefore you're looking at the correct signals that need to be measured. Now we have in the attenuation, we've got the RF level. If I reduce the span again to 1 megahertz, so in the span amplitude we've got RF level, so this will tell us what the level will be. So if we put the marker on, and then it will show the level. Now at the moment, if I just increase the span, just so that we can get rid of some of the phase noise that's on the signal from what is the signal generator over there, and we can get a more stable measurement of the level. So that's the reference level. This allows us then, obviously, if we can set this up, for example, to 0 dBm, and then that will put the, if we're giving 0 dBm out of the instrument over there, which we are doing, then the reference level now is the top line to 0 dBm, and as you can see there where the marker is, it's reading about bang on, just a little bit over, it's dithering about a little bit with the phase of a signal. So that's the ideal position to get your signal that you're measuring in. and obviously depending on the level of signal coming in will depend on where we set the step attenuators. And you obviously can set that attenuator to automatic or manual. You've got logarithmic or dB per divisions. You've got linear mode as well. So there's a bit of everything really. We've got the reference level offset, so we can offset that reference level, and then we can put in the dB in there. And I believe, although I'm not 100% certain at this stage, I think if you had a big attenuator on the front here, you can enter that level of attenuation in, and then it will take account of the external attenuation that you're adding, and then read the correct level on the screen as if that attenuation wasn't there, so that it factors that in. There's a max marker level, and then we've got amplitude units, dB, dBm, dB microvolts, so it'll read the level here, and we've got dB millivolts, volts and watts as well, so it'll read power. Obviously only up to 1 watt in this case, but as I say, with the external attenuator on there and then set in the instrument to take account of that, then it can read more RF power depending on the attenuation that you're sticking in. We'll talk about power attenuators in the later part of this video as well, and making RF power measurements directly or indirectly via sniffers. Okay, one of the other functions as well that we have is sweep mode. We've got bandwidth, trigger, auto couple, trace and display, so we'll have a look at these next. So in the sweep mode, we've obviously got sweep time where we can set it automatic or manual. We can make adjustments there. We've got a sweep whether it's continuous or single, so that's a single sweep again. We've got a gate on and off as well, gated video, and then we've all got different options in there. We've got the sweep time, 2 microseconds, so using the step up and down we'll be able to set the different sweep times. And then we've got the sweep on and off there, DLY sweep. Under bandwidth, then we can we've got resolution bandwidth, auto, manual, video bandwidth, resolution bandwidth ratio, resolution bandwidth span and ratio, video, AWG on and off. Not sure what that does. So it cleans up the video a bit. So then we can have a look at trigger, for example. Video line, sweep, single, free run, external. So there's all sorts of little video trigger level 0 dBm, free run. So you can set up all kinds of different things there. On the line, not sure what that is, but video, you can set up a predetermined RF level, and it's put these little dotted lines there, which means anything above that will trigger it, and you can set up a level there. Trigger pole position and negative, positive and negative. So there's all sorts of different bits under there. Auto couple, as you can see, multiple things there. Attenuation, auto, manual. So you can have that moved into auto manual mode, for example. Center frequency step, limits. So there's a bit of everything there. Auto couple, trace, So this is where we can take a signal, we can max hold A, okay, then we can view A, and then we can do a trace B. So for example, I could reduce the RF level now on the signal generator, to give you an example, and then I could do trace B, max hold view B, view right B, max hold B, there we are, and then we could view B. So basically you can make a comparison between the previous signal and the signal as it is now. So with that modulation, amplitude, whatever, you can make measurements of before and after, or differences between different signals, or different parts of the measurement with an amplifier on or off, and then calculate the gain. You can do all kinds of different measurements within there as well. You've got various detector modes, A exchange with B, so I think you could effectively put that round the other way. You can move a marker from one to the other. Not sure what detector modes are. Detector normal, detector sample, detector negative peak. So there's all kinds of different things that you can go into in there. And then on the display, we can alter things like the intensity of a display, screen title, threshold, display line 0 dBm at the top, so for the reference, frequency DSP, I think that's a digital signal processor, great on and off, anot help, focus, so all the focus controls are all there as well. So there's quite a bit, you know, that can be looked at. So that's a rundown of the control there. The next thing I want to look at is just how you look at the 3 dB points now of a signal and calculate bandwidth, etc. So that's what we'll look at next. Yeah, one of the other little clever features that there is on this spectrum analyzer is the ability to track a signal. Now that's governed by the span. So under the markers menu, it'll then display this side menu here, and there's one called signal track, on or off. So at the moment receiving a signal on 150 megahertz. Now if I flick that to on, because that's obviously the centre of the screen, providing the frequency moves within the span, which I've set to at the moment a span of 200 megahertz, if that frequency moves anywhere within that 200 megahertz span, then it'll track it now and it'll find it. So as an example, I'll set the signal generator now to something like say 150, set it to 200 megahertz. So at the moment obviously it's 200 megahertz, and then what it'll do, it'll grab it. You just saw it there, the frequency moved further up here to 200 megahertz from 150, and what it did, it grabbed it and then pulled it to the centre of the screen. So for example, I could put in say 160 megahertz in now as a signal going in, and then what it'll do, it'll grab it and pull it back. Now obviously with signal track off, if you were to then move frequency again, say if I put in 170 megahertz now, then it would obviously move without tracking it. Now the only issue with that is what I spoke about right at the beginning of the video, was if you've got full span of the instrument, so from, you know, 30 Hz to 2.9 GHz in there. We talked about the internally generated frequency, which is actually representing 0. What happens is if that signal tracks on, depending on the software version that's in the spectrum analyzer, some of the older spectrum analyzers, like this microwave spectrum analyzer that I've got up here, which goes up to 22 GHz, that particular one isn't as intelligent as this one. So what happens is when signal tracks on that, if you remove a signal here, what it does, it immediately goes to the internally generated frequency and locks onto that, and then you start your measurement again, and it confuses you until you look at what the frequency readouts are, and without realizing it, it's at the speed of light moved on to the other frequency and tracked to that as soon as the signal input goes off here. And then it messes up your measurements because you're not looking at the signal that you're actually putting in here, and it's, you know, later on you realise, and then you slap yourself on the head and realise what's happened. But in this particular software version that's on this 8560E model, I think the A model does suffer with this, but the E, this one, has got a higher level of software on it. It's taught to then ignore the internal birdie frequencies, the harmonics, the internally generated signals, so it doesn't include it as part of your measurement. But not all spectrum analyzers do that in the HP range, so beware of that. Likewise, it will only track signals that's within your span. So if you've entered a frequency, for example, that's coming in that's outside of the settable span, it won't track to that. So obviously that's something that you need to be aware of. But it is a bit of an awkward feature because it's useful in some respects and troublesome in others, in the fact that it can lock onto all kinds of things that you don't want it to lock onto, and then unless you keep an eye on what the centre frequency is down here, you might find it wandering all over onto different things, depending on what you're feeding into it, of course. At the moment we're only feeding in what would be effectively a sample from a transmitter or a signal generator, but if you were looking at off-air signals, for example, and you'd locked onto a frequency because you were looking at an antenna input here that's being amplified, so you can pull off what's on the radio spectrum. The moment that signal goes off, it'll then lock onto the next one or the nearest one, and then it'll move about, and it can be a bit awkward. So that's probably switched off when you're looking at off-air signals, because it'll be going all over till it locks onto something that doesn't switch off or go off in signal context. So that's just a little rundown of that feature. Okay, so I just want to do a little feature now on delta markers, where, for example, we're wanting to find out, say, the bandwidth of a signal, or we want to be able to look at a reference point and compare it with another point on the signal diagram. So at the moment we're modulating a radio frequency carrier with a frequency modulation, and currently we've got 10 kHz deviation at 1 kHz tone. So we're frequency modulating the carrier to a level of 10 kHz with a 1 kHz frequency. So that's basically what we're doing there. Now if we go to markers, obviously I've set the span up as well so that we get a good picture of a signal that we're looking at, and you can select normal marker, and say we're wanting to find out, for example, the distance or the deviation width between this point here and that point there. Then first of all we can get this marker, the little ball, under normal marker, to move over to that peak, for example, if we're happy it's positioned correctly, and at that stage it gives us obviously the frequency and the level that it's recording. Now if we switch to delta marker, so that will be our reference point, switch to delta marker. Now we're shifted to delta marker, so we're at 0 Hz, that's obviously the reference point, that's where we're starting from, and the level, for example. And now if we move the rotary control, so we get that little ball to track all the way over to the right peak, over to there, just about, then that will tell us, for example, that from that peak to that peak, as it sees here, is 16.7 kHz, and it says it's reading well, it's varying between -1 dB and plus 1.5 dB, 1.16 dB due to the modulation. So that's an example of how we can measure something. It doesn't matter where you move that ball to, it'll always use that as a reference. So you can, you know, make measurements wherever you like and get all kinds of useful information from that. Now there are different modes within that delta marker as well. It'll tell you the time, the signal track as well, whether you want that on and off, all the markers to be off. So there's that feature as well, which is quite useful. Now, as well as the capability of looking at RF signals, as we see there on the screen, we can also demodulate them, and we can listen to them using the volume control. And how we do that is we select here this key, AUX control, and then within there, as well as the tracking generator option that we're looking at shortly, we've got the AM and FM demod. So when we select that, for example, we can demodulate AM or FM signals. So if we switch FM demod on, we can hear the signal being demodulated. Now it's switching on and off because every time it does a scan, it switches a mod off while it takes a snapshot, and then it'll allow the audio to come through. But you can change that by going to demod time. At the moment it's set to 1 second. So if we adjust that now, then obviously you can see you get a shorter snapshot, or you can get a longer snapshot depending on what you want, or I think it'll even go up to higher than that, 60 seconds. So you can do all sorts. You've got swatch control as well. We can set the RF level with the rotary control, or the settings. You've got AGC for AM or SSB signals. So there's quite a bit there with it as well. So you can obviously demodulate both of those. As usual, you've got your peak search facility. Next peak, you can select different peaks. You know, obviously get the marker to move with it as well. So that's a little rundown on the demod capability within the instrument. Right, we've got an experiment set up now. We've got the tracking gen option we're going to be looking at now. We've got a UHF filter here which is tunable with these slugs, and we've got that obviously connected to track gen output to one port, and then the other port obviously connected to the other side of the filter. So to get to track gen option on a HP8560E or A model, first of all you have to hit this AUX control, and when you do that then it brings up this menu here. So we've got the tracking generator function. Now obviously at this stage we can set up a measurement quite simply by using the frequency control now as well. But we'll set up SRC power, search power is on. You can calibrate these two together, run a cal sequence. You can do that if you want. So you can do a through cal, a cal open short, and also recall a through or recall an open short calibration. So you can do the calibration between these two ports first. Obviously if you've done this earlier and saved it, then you obviously wouldn't need to do that now, but just for the sake of this video I'll go into that, and then at least you can see it being done. So without anything connected to the ports at the front, what we need to do is there's the we obviously have the cal output, and we're not using that in this context. What we're doing is we're connecting this port to that port, and that's what we're going to be doing now. Now obviously it's going to set up a signal level at a particular frequency, or a group of frequencies, and then it's going to run through that group of frequencies and levels to then calibrate the instrument appropriately. So we have a short cable. It's important when you're doing these kind of calibrations that you don't have ridiculously long cable, obviously, because all that's going to do is just make the attenuation of a signal more, and therefore the measurement won't be as accurate. So it's better just to get something that's, you know, less than 30 centimeters long, and just with good coax, not this rubbish that you sometimes get from China and places like that, where it's leaky but very low loss coaxial cable. Some would even use the solid coaxial cable that's like copper tubing, that kind of thing, for the serious connoisseurs of calibration. But just for this particular thing, we're just using some very low loss coaxial cable there to short distance. So we'll do a cal through, and then it's doing that now, and it says store when ready, store through. Okay, now if you notice, the signal generator power is at minus 10 dBm. Normally when we're doing tracking generator measurements, we'll normally set that to 0 dBm. So if we just press, in this case, 0 and then dBm, then it will now set that up there. And we can do another source cal through, store through. Right, if we set here the amplitude 0 dBm, we notice that it's not reading the reference level on the top line, and there's a good reason for that, and this is where people sometimes make mistakes with the measurements that they make, and I'll show you that next. And maximum marker level. Right, so we'll go back to AX control, tracking generator, and then we do the manual track adjust or tracking peak. So in order to get these levels to read properly now, because we've calibrated it, we're giving a 0 dBm output from there, and it's coming back into here. And the reference level for the top line is set at 0 dBm, but the trouble is that, as we can see, the signal isn't there. So how we get that back, and this is where I've been contacted by numerous people who have got these spectrum analyzers who say, look, I'm putting 0 dBm in, the filter that I'm adjusting isn't giving me 0 dBm back in the tuned band, or near 0 dBm, or when they connect the cable directly across the input and output there, they're not getting 0 dBm. And that's because you need now to set the spectrum analyzer for the tracking peak. So it'll find the optimum peak now based on the calibration data that's previously been saved in the earlier step we did, and then it'll calibrate it to 0 dBm. So it's that button there. It'll go through a bit of a sequence where it'll make a funny clicking sounds or whatever, maybe, and then it'll calibrate it right up the top there. So that's where our peak line is now, at 0 dBm, and we can confirm that because it is at 0 dBm when we put the markers on. And so the marker level is 0 dBm. So again, it's reading 0.67 dBm, so it's basically 0 dBm on that line there at the top. Now it's a bit awkward sometimes. You have to go into this menu a couple of times just to get back to where you were. Range level 1 to 3 more, normal, reference position, normal, normalize. So we've normalized it now. So we've calibrated the source power and the spectrum analyzer. We've then looked for the tracking peak, so it calibrates, use that calibration data to calibrate its reference level to 0 dBm. We're giving 0 dBm out. We're confirming now we're receiving 0 dBm here, which we weren't before, because the line was down here, as you could see. So now we're ready to begin measurements. It's only when you've achieved that you should go ahead and make measurements. If you go ahead and make measurements without doing that, the measurements will be wrong. So that's where you need to be. So now we'll look at the filter and connect that up, and we'll then begin our measurements. Okay, now we've done all the calibration and everything in the previous step. You'll notice now there's arrows that have appeared at the side of the top line, which indicates our reference level where we were, and as I say, we've made it 0 dBm, which is equivalent to 1 milliwatts of RF power. We've now connected up the filter to the in and out ports here, and now we're ready to do a bandwidth adjustment, or to have a look at the performance of the filter. Now we can do that by selecting frequency, and now we've got some new options that weren't available prior to activating the tracking generator under the frequency menu button, which is the start and stop frequency. Well, the frequency on this particular filter I think is set at 416 megahertz with the look of it, so I know roughly that whereabouts it is. So we could say do a start frequency of say 350 megahertz, and then we could do a stop frequency, for example, at say 450 megahertz, and then we could have a look then and see what we've got. Right, now we can adjust the attenuator, the amplitude. So let's have a look at that. So we've got something there. We could perhaps, it's a bit higher than the top line there, and then we might be able to adjust the span. Could adjust the span to something like 50 megahertz perhaps. Frequency, we'll try and pull it in a bit further to centre of a graticule. Now at this stage, what we can do, we can now either reduce the bandwidth, so we're excluding some of this side here, side lobes, or we can increase the start and stop frequencies or decrease them accordingly. Now the centre frequency is 416.750 megahertz. Does that fall in with that? 416.25, it's thereabouts. Now if we wanted to look at things like, I think it was 3 dB points, I think it was under menu, that was it, it was under the menu user button, and then now you can look at the 3 dB. If you want to look at the bandwidth at that particular filter with the 3 dB points, then it'll select that, and now you can see it's put two little dots there at 3 dB points, and that will give us the peak bandwidth of the filter, the pass band. So then it'll say basically the centre frequency being 416.75 megahertz, it'll say it's got a 5.33 megahertz bandwidth. So that's what that gives us. For 6 dB points, then it'll tell us that it's 7 megahertz bandwidth. And so again, that's useful information for calculating the bandwidth of the filter. Now we can obviously reduce the span. The span at the moment is set to 50 megahertz, so we could reduce the span to say 20 megahertz, and let's have a look and see what that's like. And then we could go back to user then 3 dB points to get more accurate information. So that gives us, if you like, the bandwidth, the usable bandwidth, and the specification of that filter. And we'll have a look now at the power menu as well. Channel power, occupied power menu. We'll look at that. Occupied bandwidth. So it gives us occupied bandwidth data. Again, it's mover marker points. So it gives you all kinds of useful information at that stage under the measure menu, obviously of what the bandwidth capabilities are of this particular filter. And we can adjust that and tune that to whatever frequencies that we want, and that obviously would then we can look for the right performance and characteristics in the filter when we're making the adjustments, and right shape of the waveform so that it's nice and flat, stable like it is there on the passband area, and not jerky or loby or peaks and troughs in it. So we can do all kinds of fancy things. But that's a little rundown on the tracking generator insofar as looking at a filter, a cavity filter for UHF. Well, I think I've upset it now. This is one of the things that I don't like about the HP spectrum analyzers. They don't seem to have like an exit button. So what I did, I went through these 3 dB point things in the previous section, but then I pressed this, and when that happened, it came up this error 902 bad norm. Well, I can't get out of that. No matter what I do, I can't press anything to get out of it. So basically, your best friend is going to be the preset button, and then basically just start again. Well, that's basically what you have to do when you get locked out like that. Just go right back to the beginning and just start all over again. So basically, to recap, regards to the tracking generator, it's under the AUX control, then select tracking generator. To actually activate the output port to get RF to leave there as part of a signal generator, tracking generator, the search power, SRC power, needs to be in the on, and when that's selected to on, it's starting to produce a signal out of here. The other thing to bear in mind as well is when you do your calibration, your source cal, after that you need to do tracking peak, which is this button, and that will then set it up properly, and it'll obviously put your markers in the right place, well your reference level in the right place, and it'll set everything up. Remember to use 0 dBm as well. If we go right back to the start, it says there tracking power. Now whenever that message is displayed on the screen, that's at the point where you can enter any level. For example, you could put -10 dBm in, and it'll now use that. Did I put the right level in there? Yeah, put -10 dBm, and it says -10. There we are. Don't know why it didn't like that. I pressed minus there 10, and then press the dBm button there, and it set it to 2 dBm. Why that is, I don't know, but anyway, if you type in 0 dBm, that seems to work. And so there you're setting the level up. If that level's too low, then obviously you're going to need the input attenuator, the amplitude, the step attenuator adjusted so it's more sensitive, and it can cause problems with your measurements because all filters have losses, band pass, band reject, band stop, all those, they all have things. If you're aligning a duplexer, you're tuning one for a pass band and the other side for a band reject or a frequency reject. So you need to know your starting and end points, and obviously if you're outputting a signal that's say -10 dBm and your filter's reading -60 dBm reject, for example, is it reading -60? It's actually might be -50 dBm because you're starting with -10 to start with. So mathematically it can get a little bit weird. You start racking your brains a little bit trying to make sure that you've got the right measurements. So if you start with 0 dBm and it's calibrated to the top line, then that's that's your starting point, where you are. So that's where most people go wrong, is not setting up the spectrum analyzer and the tracking gen properly in the reference levels, failing to do the calibration, failing to then check when they have done a calibration with the two ports linked together that the levels are correct, and they go straight away into making a measurement without doing the all important tracking peak, which then calibrates the instrument and sets it up properly. Otherwise then the levels will be off, as you saw earlier in the video. So just be aware of that. And the schoolboy errors, it's very difficult to get that information from the manual, because it's only through using it that you'll get to know that. But it's like a dominoes, you know, if you don't do one right, then you know the rest of them will be wrong. Okay, I just wanted to talk briefly about how we could measure signals from a high power transmitter on a spectrum analyzer. Now, as far as measuring high powered signals, generally the industry standard is to use what's called a directional coupler or a sniffer, and these come in all different shapes and sizes and frequency characteristics, but basically the principles are the same. Within the device we have an input and an output which is coupled straight through, and then we've got another transmission line which runs in close proximity but not touching this transmission line here, and the two would couple to each other in a loosely coupled way, and in this case, as indicated on the label there, it will be minus 20 dBs coming out of this port here. So we would obviously, if we were, say, for example, measuring a transmitter that did 500 watts RF power, we would typically use an RF power meter separate, such as this Bird 43, a high powered RF load that will connect into the Bird meter, and then on the input of the RF power meter we would then connect the directional coupler, and then on this port here we will then connect the transmitter. So as far as the transmitter is concerned, it's seeing a 50 ohm load directly through the watt meter, and obviously we can read the RF power on there, and in addition to that we have a minus 20 dB coupled output then, which we can feed off then to the RF signal generator. Now in rare cases where we're measuring extremely high RF output powers, you know, up to say several kilowatts, several thousand watts or whatever, then we can reach into new heights where we have other problems, such as the coupled RF output might be too high then for a signal for a spectrum analyzer to cope with, because obviously if we're reading 7,000 watts through it, minus 20 dBs of 7,000 watts can actually be quite a high level of RF, which would exceed 1 watt on the input there and damage it. So you might then need to use additional attenuators, or if you have them, a directional coupler with a higher isolation, so as to combat that. And there are people that do measure high powered signals like that as well, so you know it is common practice. So we would connect the output then obviously through another attenuator into the input. So that's where you need to be careful when you're making measurements, is your sniffers and your directional couplers and things like that. Are they providing the right level of isolation that's needed, so you're not overdriving the spectrum analyzer? Obviously the power meter can read several kilowatts, depending on what pod you've got in, or 50 watts, 10 watts, 5 watts, 1 watts, whatever. And then it's into a load. The other way as well is direct measurement, where you can directly connect a transmitter into an instrument like this via using what's called RF power attenuators. So if you're reading relatively low levels of RF power, although it's not exclusively for that, but generally is, you could use attenuators such as this. Now this is an RF power attenuator that's only rated at 3 dB. You can buy them in different levels of attenuation, and they will connect on directly onto the instrument, and then you will then connect your transmitter onto here. Now this is where you've got to be very careful that you'd obviously choose the right attenuation. As I said earlier, that you know, for every 3 dBs you attenuate a signal, you half its power. Now bearing in mind this is a 1 watt maximum input level. if you were to use a 3 dBs, the maximum RF you could stick in there before it damages it would be 2 watts, because obviously it would half its power to 1 watt when that's applied. So you know, you would need to choose an attenuator. If you're measuring a 5 watt transmitter, 10 watt, 25, 50 watt, you'd need to get the appropriate level of attenuation before you made that measurement, and you'd have to be certain that that's the case. One of the ways that you can check that is by connecting the output of attenuator, for example, into an RF power meter before you connect it to the spectrum analyzer. Transmit into it and then just check that the RF power reading on the meter is within the tolerance of the input power rating on the instrument you're going to connect it to. So again, that's something that you need to be aware of. Now, this is a small signal attenuator. Something like this can handle up to say 1 watt or 2 watts typically. Now that's a 3 dB attenuator and that's a 3 dB, but that can handle like 20 watts of power. That can only handle 1 watt of power. So though they've got the same level of RF attenuation, they are actually totally different insofar as power handling characteristics. Again, this is another example of an RF power attenuator. That can probably stand about 5 watts, maybe 10 watts continuous. And that has a particular level of RF. Some are printed on the connector, others have a separate label on. Some are rated for microwave frequencies, others go up to 1 gigahertz. This is a particular attenuator here with the SMA on it. This goes up to 18 gigahertz. This is via mini circuits, and then they have a level of attenuation printed on them. This can handle 2 watts, I think. So again, you know, you get different classifications of RF attenuators. And again, we've got things like this from radial. This can be bolted to a heatsink. That's why it's got these screw holes underneath it, so it can be fastened to a big heatsink. And that is a 3 dB attenuation at 16 watts. Another thing that you need to be wary of with attenuators is some of them, not all, but some of them are manufactured so that they have an input and an output port, and some can be the reverse of what you think. So you need to check that. Some will say in on the actual connector, or they'll have a label on, or out on one side, so just be aware of that. If you get them the wrong way around, they can have a wrong attenuation and you can burn them out and damage them. This particular type of, that must weigh about 500 grams probably, so it's quite heavy, a lump of metal. That'll bolt to a heatsink, and then you can pass up to 16 watts of RF through that to get 3 dBs attenuation. So you get the picture. There's all kinds of 50 ohm loads. There's this type of 50 ohm load where it's only got a connector on one end with heatsink fins on. There's oil filled, clear the oil in that's by Bird, I think. There's then other types of terminating resistors as well. There's loads of different examples here. Again, this is a very expensive microwave type RF attenuator where you can dial the attenuation on there, but that can only handle maybe up to 1 watt of RF. So again, you need to be mindful of the application that you're using. But if you want to measure power directly into there, you can do so, but you must make sure you've got the right attenuator on for the job. Likewise, within the spectrum analyzer, there's an external attenuation facility as well. If you remember when we were in the markers, you could then select power. Well, if you enter in the minus 20 dB level that this would give, for example, then that would obviously calibrate this so that whatever RF attenuation this makes for, it would then reinterpret that as RF power. So it would then be able to give you an RF power reading on here in watts, even though it can't take more than 1 watt up here. By taking into account the attenuation that you manually enter in as an offset, it will then give you a reading on there as to what power it's sniffing and what that would be if it was directly connected to a proper power meter. So you can do all that kind of thing as well. But generally speaking, if you're doing high powered RF measurements, doesn't matter if it's digital power measurements, analog power measurements, I have a Bird 5000 EX meter as well, which measures digital power, and this is an analog, obviously, meter, which is particularly used for all kinds of different applications. But again, you can stick as much power as you want into that, and the nice thing about it is we're just sniffing off a signal to the spectrum analyzer, and it protects the instrument, and obviously you can measure the power directly on this meter as well. So there's all kinds of different attenuators and what have you. So it's just being mindful of what type of attenuator you're going to use for the job, how much power it's expected to take, how much heat it's expected to dissipate, and likewise as well, when you're using attenuators, make sure you get the input and the output right, otherwise you can cause damage because obviously the attenuation won't be correct. And make sure you just choose the right attenuator for the job. So right, we'll get on with the next section. Okay, one of the other things that just to make you aware of, which is a feature within the tracking generator, is you can also do reflection measurements using what is obviously a directional coupler or a directional bridge, reflection bridge, where you can calibrate the under the source cal. You can perform all your source cals with your open, short and through using this in conjunction, and then you can calibrate the output port so that it gives a flat response when it's into a 50 ohm load across the screen, and that way when you remove a 50 ohm load and connect that to, say, an antenna or a device where you want to measure its VSWR or its voltage standing wave ratio, or SWR, standing wave ratio, you can measure reflected signals coming back as an antenna analyzer, for example, and it will then give you the level of reflected signal coming back. But you have to connect this in a certain way and calibrate it through the spectrum analyzer, so it takes account for this directional port. Now if it's that way around, then obviously, depending on where this port is, this port will always sniff power closest to its input port. So for example, if we've got an RF signal coming in this way, it's travelling in from left to right direction, from the in port to the out, and this has terminated into a 50 ohm load, for example, then this port here will measure the forward power. This side is a 50 ohm load, so the internal line that goes to a 50 ohm load comes this way and goes up to there, and it runs close proximity to the line that's going from the in to the out. So RF power travelling this way from left to right is more coupled onto this line in that fashion. So therefore this will read forward power as it's configured now. Now if we turn it the other way around, and then obviously we have the 50 ohm load here, for example, and the signal source coming in here, so this is in and out. Now when the 50 ohm load is on, there'll be minimal couple up to this port in that configuration, and so basically what would happen is, where it's perfectly matched, there'll be no reflected signal going back the other way. And when we remove that 50 ohm load and connect it into, say, a mismatch load, such as an antenna that's working on a frequency that's not designed for, or some other open circuit or short circuit that might be present in a transmission line, for example, like coax or whatever, then any reflected signals coming back that way will be coupled onto this port more readily, and therefore that will read reflected power more than it will read forward. So the idea is, of course, is that depending on how you orientate this in line with the spectrum analyzer, the track gen option on there, and calibration procedure will depend on which way around you have it, will depend on whether it's reading forward or reflected power. And so by calibrating this in with the track gen, you'll be able to measure reflections as well in various systems, so that's just something to note. I did do that earlier, calibrated it with it, but I've not read the manual sufficiently enough to understand how you get the line to stay flat. But just a quick example of how I did it was that I had a this connected onto there as it was, basically, so that we were reading basically reflected signals, because the port on the output of the sniffer or directional coupler is closest to the antenna side, or the side that we would be connecting our antenna to, or our mismatch load to. And then what I did is I calibrated the instrument. I did the open, short and through path cals, but then I did a calibration connecting this port up to there, putting this into a 50 ohm load, and then it basically did a calibration of that as it was set up currently. So if I just connect this back up, so we have this port here. Let's have a look. Got so many things going on at the moment. Let's have a look. There we are. Right, I've got that 50 ohm BNC thing there, which is fastened up. Right. So what I did, I put the 50 ohm load on the output of the reflection bridge. I then connected the spectrum analyzer signal input there to that adapter, connected one end of the adapter to the cable, obviously. So we're generating a signal coming out of that port when the tracking generator is enabled, gets dumped into this 50 ohm load, so there's very little reflection coming back. Now, I can't remember if I'm doing this right or wrong. It's one of these things where I haven't done it in a while. I just wanted to give you a rough idea of how it's performed, and obviously then with your particular example you'll be able to I might have got it the wrong way around actually, but as I said, without reading the 1000-page manual. But basically I went to tracking generator, we turned the tracking generator source on, we then went to can't remember if it was source cal. I did all that earlier, so I don't need to go back to that. That were it. We did the tracking peak, and then basically it did its thing, and then we had the if I remember rightly. Now if I remove the 50 ohm load so we get reflections back, then you can see that we're getting obviously power reflected back coming back in, and that's giving us that response. So I did something like for example frequency, start frequency, say 1 gigahertz, stop frequency 1.5 gigahertz. To have this sort of line, and then if I went to tracking peak again, see it puts it straight, the line, and well, more or less, but defaults to that. But I just can't figure out how I got it to. I did do this a while ago, and I can't remember how I did it, but I managed to get it so that line was flat across the top, and then it gave a response obviously there. 50 ohm load, and so that's reading, you know, a reflection basically. So once you remove a 50 ohm load, the reflection is then captured on the scope as a reflected signal, and there is a way that you can get that to read then in VSWR and reflections. So it's just a case of getting deep into the menus and setting this up properly and calibrating it so that then it gives a VSWR reading as opposed to a level. So yeah, that's something else that you can do with these spectrum analyzers if you didn't know that. Okay, one of the last things that I want to discuss before we come towards the end of this video and we look at the rear panel and some of the features on the rear is I just wanted to have a quick chat about resolution bandwidth and where we can have issues with more than one signal being present in the input but yet appears on the screen as being just one signal, as we can see here on the display. I'm actually putting two signals in at the moment on two separate frequencies. However, it's appearing as just the one peak in the middle of the screen. Now, just to give an explanation of what it says in the Hewlett-Packard manual, so I'm not talking out of turn. It says here, what is resolution bandwidth? It says the signal resolution is determined by the intermediate frequency IF filter bandwidth. The spectrum analyzer traces the shape of its IF filter as it tunes past a signal. Thus, if two equal amplitude signals are close enough in frequency, the filter shapes of the two signals can fall on top of one another and appear as a single response. If two signals are not equal in amplitude but are still close together, the smaller signal can be hidden under the response of the larger one. So that's what's occurring here. Now, if we look at the bandwidth mode, which is the BW button, we've got the resolution bandwidth at the moment set at 1 megahertz, but we can manually adjust the resolution bandwidth. That's at 2 megahertz, so that's the maximum it goes up to. Then we come down to 300 kilohertz, 100 kilohertz, 30 kilohertz, 10 kilohertz, 3 kilohertz, 1 kilohertz, and then we're down to the hertz range. As you can see, we can't seem to pull those signals out. So I'll leave that at auto. We'll go to the span, and what we'll do, we'll just reduce the span now to 200 megahertz, and we still look like we've only got the one signal. And then the span here to 100 megahertz, and now we're beginning to resolve that there. Now if we go back to bandwidth a second, and then we go to, so again, you know, the 2 megahertz resolution bandwidth, it appears as one signal. At 1 megahertz resolution bandwidth, again looks like it's one signal. 300 kilohertz, and then we can start to see at 100 kilohertz it's resolving both signals, and now we've got at 30 kilohertz the two signals. So that gives you an example really of what can happen when you've got multiple signals at higher resolution bandwidths. They appear as one signal, so you need to look out for that if you're dealing with multiple frequencies at close proximity, and that's how sometimes things can get hidden from you. So it's just a little example. As well, when you're dealing with harmonics, if the bandwidth is too wide, if you've got multiple harmonics because you've got a dirty transmitter, sometimes the harmonics can get hidden as well if there's multiple harmonics or frequency instability around the fundamental that you're looking at. So again, that's something that you need to take into account, is adjust your span and your resolution bandwidth accordingly so that you can resolve any signals that are present. And already it appears like we've got a mixing effect here of the two signals mixing together, which is producing a harmonic. So if we go to the amplitude, we can see we're starting to pull out a harmonic there, at that frequency as well, so we can use the marker and we can use the frequency counter as well. There's a frequency counter on here somewhere. I'll find out where it was. I've seen it somewhere, unless it's under might be under display. Maybe not. I have seen it where it does give a frequency counter output as well. Frequency control. Counter on and off, there we are. So that's a frequency there. Have that harmonic at 502 megahertz. So it gives you a little example of what happens when you know, you have two signals very close together. Okay, this is the rear of the unit. This one's fitted with a mass memory module option, which is this device, and there's a slot in the top for a card, I think, to plug in. I've never had one of those, I don't think, for one of these, but you know, they're probably out there somewhere on eBay somewhere. But yeah, so on the rear we have I think this is the GPIB, yeah, that's the GPIB interface, general purpose interface bus. Then we've got the video output, which will be a 75 ohm CRT RGB video output. I'm sure you can get modern day converters now from what is CRT to HDMI or SVGA, VGA converters. They'll be out there, because gone are the days now where monitors are made with standard CRT inputs. You know, they used to be years ago when this was first produced, but not now. Then we've got an external gate trigger input. We've got another gate output there, so we've got an input and output. We've got the IEC with the fuse, and then down here we've got the local oscillator sweep output. So if you use an external sweep oscillator, for example, which you may do, for example, it could be on a higher frequency, then this spectrum analyzer could go up to something like 20 odd gigs, for example. You can use a mixer as well then on the externally, a separate mixer to then mix with that oscillator's output and a local oscillator that you can produce from this with a track gen, and then you can then mix down convert microwave frequencies then on a sweep generator to then read on the scope, so it can extend the frequency capability of the spectrum analyzer by doing that. And mixers are readily available. I have a number of mixers which go up to, like, I think it's 18 gigs or something like that, which can be connected externally to the instrument. We've got an example of a mixer here. These are some mixers, and these can be used externally. These go up to about 18 gigahertz, and also there are other types as well. This type, for example, this is a Magnum double balanced microwave mixer, and that goes up to this particular one, I think, goes up to 15 gigahertz, that one. So you can use those externally, obviously. Use that then to drive an external sweep oscillator, you know, that could be on the higher frequency ranges, and then mix the signal output of that with a local oscillator of this to produce an IF, if it'll do that range, in the IF range of this, and then you can down convert as well. So it's fairly useful to do that. Or alternatively, you can just drive an in-band sweep generator that's in the same frequency band as this. If it didn't have a track gen option on it, for example, they all tend to have that output on them anyway, whether they've got the track gen on or not. And then you can use an external sweeper. There we've got I think it's a 10 megahertz reference oscillator in out, so you can feed in there from a rubidium frequency standard or an atomic frequency standard or a GPS locked frequency standard 10 megahertz signal to lock the instrument to high frequency accuracy, or you can take a sample of this out and then naturally read that off then to another instrument and couple it off so that you can have two instruments, or as many instruments as you want, all running on the same frequency standard that's running in here. That's blanked off, that would be the second IF out. That's the ALC, the automatic limiter control external input for the ALC. We've obviously got the fan, and I believe, not sure what that is there. I think that's an adjustment hole, probably for the frequency standard within the unit. And that's about it really. There's nothing else on it. It's fairly inconclusive, but it's just a basic back panel that you'd see on most spectrum analyzers. So yeah, well, thank you very much for watching the video. It's certainly been an interesting time playing with the HP spectrum analyzer, and it's nice to see, you know, that some of the functions and things that capability that this very professional instrument can reach. And if you like the video, please subscribe. There'll be more repair videos and demos of radio testing instruments. And so with that, thank you very much for watching, and we'll see you in the next one. Bye bye.